Hello, my name is Benjamin Gorneau, and today I'll be presenting a selection of interesting topics, including processes, tools, and techniques that are used in design and manufacturing. Here are the 5 topics I've chosen to talk about today. 3 are the bulk deformation processes of forging, rolling, and extrusion. I've also selected the strategy of using reconfigurable machine systems as tools and the technique of surface treatments as they relate to tribology. These diagrams are great examples of these processes, strategies, and techniques as they relate to design and manufacturing. Forging is a process where compressive forces shape metal by deforming it under high temperatures. With applications in creating high-strength components such as gears, crankshafts, and aerospace parts, there's many different methods of forging. Open die forging typically uses hot working and large deformations with simple tools like flat dies, rounded sections, or saddles. In a common process called upsetting, a cylindrical workpiece is placed between 2 flat dies to reduce its height. In impression die forging, the workpiece fills the die cavity shape as it deforms, forming a flash where material flows outward. The flash gap is critical as high pressure in this area ensures the die is fully filled. Closed die forging creates no flash, with the workpiece entirely enclosed by the dies, making it ideal for producing complex shapes in high volumes with precise material control. A variation of closed die forging, called orbital forging or rotary forging, brings only part of the workpiece into contact with the die at the time, and is often used to form parts like gears, wheels, and bearing rings. I like forging because it refines the grain structure of metals, significantly enhancing strength, durability, and toughness. This process is crucial for parts that must endure high stresses. Combined with the many different applications of forging, the versatility and improvements in metal properties is very valuable. Forging excels in producing high-strength components with excellent mechanical properties. However, the process is very energy-intensive. It requires significant setup costs and often lacks precision of other manufacturing methods. These 2 diagrams show the grid deformation and upsetting on the top, and the produced grain flow lines after upsetting and open die forging between 2 dies. Rolling is the process of reducing the thickness or changing the cross-section of a long workpiece by compressive forces applied through a set of rolls, passing metal between rollers to reduce thickness and achieve a uniform shape. Rolling accounts for about 90% of all metals produced by metalworking operations, for manufacturing sheets, plates, and structural steel components. Cold rolling in particular is valuable for creating surface finishes and tighter tolerances. Rolling is foundational in manufacturing due to its efficiency and cost-effectiveness, particularly for large-scale production. It enables the production of materials that are strong and precisely sized. Rolling can produce long lengths of uniform material with improved strength due to strain hardening. This is an effective method to reduce grain size and refine the microstructure in metals, resulting in improved strength and good ductility. In this process, cast structures of ingots or continuous castings are converted to a wrought structure, as seen in the diagram. However, rolling does require substantial equipment and infrastructure and is very ineffective for creating highly complex shapes. In the extrusion process, a billet is placed in a chamber and forced through a die opening by a ram. The die may be round or of various shapes. Extrusion may be carried out cold or at elevated temperatures. Because a chamber with a specific volume is involved, each billet is extruded individually, and thus extrusion is basically a batch operation. There are 4 main types of extrusion: direct, indirect, hydrostatic, and impact. Direct extrusion, also known as forward extrusion, is a process where the billet is pushed in the same direction as the extruded material, much like squeezing toothpaste out of a tube. Here, the billet moves relative to the container wall. Indirect extrusion, also known as reverse, inverted, or backward extrusion, is when the die moves toward the stationary billet, so there is no relative motion between the billet and the container. This method is useful for materials with high friction, like when extruding hot steel. Hydrostatic extrusion is when the container is filled with lit fluid, which applies pressure to the billet pushing it through the die. This nearly eliminates friction along the container walls and significantly increases the material's ductility. The last one, impact extrusion, is a form of indirect extrusion, but it's ideal for making hollow parts where the force applied quickly shapes the material through the die. I find extrusion fascinating because it allows the creation of intricate profiles in continuous lengths with minimal material waste. It's a highly versatile and efficient process, especially for non-ferrous metals. Like I've mentioned before, extrusion is excellent for creating long, continuous profiles with a constant cross-section, offering good material properties. However, it does have limitations in terms of the achievable complexity of cross-sectional shapes, and it does require significant tooling setup. Reconfigurable machine systems are multi-axial combinations of machining that are designed to be adjusted quickly in response to changing production demands. Flexibility has become a greater need in manufacturing operations, so these systems have been constructed to incorporate modular machine elements that can be reconfigured or retooled to accommodate various parts or product types. They're widely used in industries with high product variability, like automotive manufacturing, where they allow efficient production of diverse models on the same line. These systems are primarily based off of typical machine tool structures with a 3-axis machining center, meaning there are 2 linear movements and 1 rotational movement that machining can occur on. However, reconfigurable machine systems allow for the addition of other motion, such as a second rotational movement. Another example displays a 5-axis machining center with 3 linear movements and 2 rotational movements for machining, further illustrating the flexibility of these systems. Reconfigurable machining systems allow for rapid adaptation and scalability, making it highly versatile in agile manufacturing. Agile manufacturing aims to ensure flexibility in the manufacturing enterprise so that it can rapidly respond to changes in product variety and to customers' needs. Agility is to be achieved through machines and equipment with built-in flexibility, using modular components that can be arranged and rearranged in different ways in a manufacturing plant, thus reducing changeover time. The system uses advanced computer hardware and software and advanced communication systems. However, a big limitation of reconfigurable machine systems is that they may have higher initial costs due to the need for modular design and may require skilled technicians to manage reconfiguration effectively. The design process for the creation of these systems may be time-intensive and expensive to both create and train technicians to use the system correctly. Tribology is a study of rubbing surfaces and includes friction, wear, and lubrication, as well as other surface phenomena. These 3 relate to manufacturing processes in different ways. The friction between surfaces influences force and energy requirements and the surface quality of the parts produced. Wear alters the surface geometry of tools and dies, which in turn adversely affects the quality of manufactured products and the economics of production. And lubrication is an integral aspect of all manufacturing operations, as well as in the proper functioning of machinery and equipment. These factors can all be better controlled through the use of surface treatments, especially to improve performance. Surface treatments may be applied to enhance surface smoothness, appearance, dimensional precision, and frictional properties, increase resistance to wear, erosion, and indentation, manage friction between contacting surfaces and tools, dies, bearings, and machine components, boost resistance to corrosion and oxidation, improve fatigue strength, especially in bearings and shafts, or even add decorative features, such as color or unique surface textures. I find surface treatments particularly valuable because they allow engineers to enhance the performance of materials without altering their core properties. This versatility is crucial in design and manufacturing for maintaining durability, especially in components subjected to extreme operating conditions. Surface treatments significantly improve wear resistance, reduce maintenance costs, and increase product longevity. However, some treatments can be costly or time-consuming, and certain coatings may degrade under specific environmental conditions. This is often mitigated through controlling and selecting the environment of the applied surface to ensure coatings would not degrade or to minimize costs and such.